In this video, we're going to start a new subtopic, which is how to model and solve for a transshipment model. Now, a transshipment model is still a network model, which means that it still has origin nodes and destination nodes. The difference between a regular transportation model and a transshipment model is that in a transshipment model, you have more than two types of nodes. The regular transportation model that we've covered so far has two types of nodes, the supply, or also known as the origin nodes, but they also have demand, or also known as the destination nodes. For a transshipment model, you have a third type of node which is introduced into the model, and these are called transshipment nodes. The special thing about transshipment nodes is that they have to have a net flow of 0, which means that the transshipment nodes serve as a temporary phase for the products and goods to stay for some time and then leave again. So in essence, they have the qualities of both the supply nodes and the demand nodes, but because it's not a pure supply or a pure demand node, the transshipment node stores the goods for a small period of time, and then all the goods that were transferred into the transshipment node have to leave the transshipment node and go to the demand nodes. So we're going to talk about how to incorporate transshipment nodes into your transportation models, and we'll go over some of the characteristics of transshipment models. One of the main differences between a transshipment model and a transportation model is that in a transportation model, we establish the fact that the supply nodes are going to have negative right-hand side values. That's because by definition, the supply nodes are going to always have product taken away from them and shipped to the demand nodes. So their net flow value will always be negative, whereas demand nodes are consumption nodes, so their net flow value will always be positive and a positive right-hand side. However, for transshipment nodes, since there are temporary nodes in between which store the product temporarily, their right-hand side value has to be set to 0. We're going to learn more about transshipment models once we visit an example for a transshipment model. Okay, so let's visit an example for a transshipment model. In this case, we're working with the same executives furniture company example. However, we have revised the example in such a way that now it includes a transshipment node. So assume that this is a modified version of the executives furniture company example. As before, the companies has 3 factories in Des Moines, Evansville, and Fort Lauderdale, and warehouses in Albuquerque, Cleveland, and Boston. Recall that the supply at each factory and the demand at each warehouses were shown in the slide deck for chapter 5. The original network diagram for this particular example looks something like this, where you have 3 supply nodes and 3 demand nodes. The numbers next to the nodes represent the capacity for the supply nodes and the demand requirement for the destination nodes. Now let's modify this example so that it becomes a transshipment model. Suppose that due to a special contract with Evansville-based shipping company, it is possible for Executive Furniture to ship desks from its Evansville factory to 3 warehouses at very low unit shipping costs. These unit costs are so attractive that Executive Furniture is considering shipping all the desks produced at the other 2 factories, Des Moines and Fort Lauderdale, to Evansville, and then using this new shipping company. The revised unit shipping costs have been given to you in the table that you see in table 5.2. Note that now Evansville is factory and it also shows up in the to column because it can also serve as a warehouse. Now that Evansville can serve as a warehouse too, there are two additional shipping routes available from Des Moines to Evansville and from Fort Lauderdale to Evansville, which means that we have to modify our transportation model in such a way that now it becomes a transshipment model. So let's start off with the network diagram for this transshipment model. I'm going to modify the original network model and add Evansville as a destination node as well. If I do that, my new network model is going to look something like this, where E is also a destination node. In this sense, it is a transshipment node because it's serving as a temporary storage space for goods to be delivered to the other warehouses. So now you have two additional routes, which are the arcs highlighted in red, that needed to be added to the model so that we can come up with the new optimal solution and the new optimal shipping cost for this particular example. So I'm going to use this network model to formulate my LP problem. And the first thing that I will do is define my decision variables for my transshipment model. Let's call our decision variables X, and I will give them two subscripts as usual, I and J, based on where the quantity of goods is being shipped from and where does it end up in. So I represents the origin node and J represents the destination nodes. And because I is the origin node, I can take values which are D, E, and F. And J can take values which are A, B, C, and E, because now E can also serve as a destination node where it stores the product temporarily, and then the product moves from E to the other three warehouses. So based on the network diagram, we will have 11 decision variables, 9 for the original model, and 2 additional routes available because now product is being shipped from the factories to Evansville as well. So that makes a total of 11 decision variables. The next step is to define the objective function. And I'm going to use the table that has been given to us of the shipping costs to calculate the objective function value. So the objective function will be to minimize total shipping cost, and we're going to use the coefficients given in the table to write down the function for minimization. 5 is the first shipping cost. The decision variable associated with 5 is X dA plus 4x dB plus 3x dC plus, now because we have a fourth route available that goes from Des Moines to Evansville, we will add that to our objective function, which makes it 2x dE. We did not have this decision variable in our original transportation problem. This is new to the transshipment model. And then we're going to continue to add the coefficients for the remaining decision variables as well. After we have written down the expression for our objective function, we're going to move on to our decision variables. And for the decision variables, we're going to use the network diagram to help us come up with the constraint equations, which are the net flow balance equations. And just to recall, the net flow balance equation was net flow is equal to the inflow for each node minus the outflow. Let's pick node D. For node D, I'll use the inflow minus outflow part of the equation on the left hand side and keep the net flow part of the equation on the right hand side. The inflow into D is 0 because D is a supply node and there is no arrow that goes into D, which is why the inflow in D would be 0. The outflow from D would depend on how many arrows are coming out of D and which nodes are they going into. So because there are 4 arrows, the 3 green arrows plus the new red arrow that goes out of D, you're going to have 4 terms for the outflow from node D, which includes X dA plus X dB plus X dC and finally X dE. And this needs to be equal to what the capacity at this supply node is, which is equal to 100. And because this is a pure supply node, we're going to put a negative sign in front of it. This is going to give us the first constraint equation for the model for node D. Now let's write down the constraint equation for node E, and again write down the network flow balance equations for the next node, which is node E. And E is a special case here because it's a transshipment node, which means that it can serve as both a demand node as well as a supply node, since shipments will be flowing into E as well as out of E. So I'll write down the net flow equation here first, which is inflow minus the outflow is equal to the net flow. Now the inflow into E is given by the 2 red arrows that are flowing inside E, and those 2 arrows refer to the decision variables X dE plus X FE. Oops. Yeah, this is better. And the outflow from E is given by the decision variables. I'll put them in the next line. XEA plus XEB plus XEC, and that's it. Now notice that we did not add the decision variable XEE because that decision variable does not make sense, since the warehouse and the factory both are located at E, so you wouldn't have to ship anything out of the factory and into the warehouse. It's within the same location. And this left hand side of the equation would equal to the net flow for E, which is originally a factory and now has been converted into a warehouse. So the net flow for a supply node is equal to the capacity of that supply node. So in this case, the capacity for E is negative 300, That comes from the fact that it is a supply node. And the net flow for a transshipment node comes to the value of 0 because it's a temporary node. It just stores the product temporarily. It does not produce anything. It only stores it and ships it back to the warehouses. So the net flow for a transshipment node should always equal to 0. But because E is a special case and it's a supply node and a transshipment node, we would add the net flow of 0 to it. That does not change the right-hand side value, and it keeps it at negative 300. But this is just to make sure that if you have another example or another problem where there is a situation like this where the node is a supply node as well as a transshipment node, then you would do the same procedure for that node as well. So following the same methodology, we have the full transshipment model as minimizing total shipping cost, which includes the two new decision variables, DE and FE, subject to the net flow balance equations for each node. The only node which is different here is node E, which refers to the Evansville supply and transshipment node because it has an inflow as well as an outflow, and the net flow is set equal to the capacity of Evansville as a supply node. Let's move on to Excel to get the solution for this particular problem. I've created a template here, which I'm going to fill out with formulas and numbers from the examples so that we can get to the solution for this particular transshipment node. One thing you can note here is that in the earlier transportation problem, you had Des Moines, Evansville, and Fort Lauderdale as the supply nodes and Albuquerque, Boston, and Cleveland as the demand nodes. Now we have added Evansville as a demand node as well because it's serving the purpose of a transshipment node, which means that shipments can go into Evansville as well. So I've added the shipping costs in a separate box of cells down below the decision variables. And as everybody knows, the first box of cells here would refer to our decision variables, so I'm going to highlight them in yellow and we will leave those blank because Solver is going to populate these values for us. Now let's come to the objective function. The objective function of the problem is to minimize total shipping cost, and that will be the sum product function of our decision variables with our shipping costs. And just so that you get the formula correctly, it's the sum product of the cells in yellow with the shipping costs. And because this is our objective function that we need to minimize, I'll highlight this in green and put a min in front of it. Now I'm going to calculate the flow out of each of the demand nodes by calculating the sum across the columns, and I can drag this down to get the sum for each of these three supply nodes. Finally, for the demand nodes, we will calculate the flow into these demand nodes by calculating the sum down the columns. And I can drag this across to get that sum for each of these destination nodes. And here we're going to use this box to help us form the network flow balance constraint equations. Now the flow into Des Moines is equal to 0 because Des Moines is a pure supply node and there are no arrows flowing into Des Moines. The same goes for Fort Lauderdale. Since there is no shipment going into Fort Lauderdale, these two cells would just be equal to 0. Evansville, on the other hand, has inflow from both Des Moines and Fort Lauderdale, and that's equal to the sum that we calculated in E8. So I'll put that equal to E8. And just to make sure that this 0 is different from the other two zeros which I added manually, I will highlight this in blue so that I can remember that there's a formula in there, which is why you see the 0 and not because this 0 was added manually. Now let's go to the outflow for each of these supply nodes. For Des Moines, the outflow is equal to the value calculated in cell F5. And for Evansville, it's equal to the value calculated in F6. Whereas for Des Moines, it's equal to Fort Lauderdale. Sorry, for Fort Lauderdale, it's equal to F7. And the net flow is just the difference between the inflow and the outflow. And I'll drag this down all the way without formatting. Now, because each of these new cells that I filled in have formulas in them, I'll highlight them in blue as well. Let's move on to the demand nodes. For Albuquerque, the flow in is equal to the cell B8, where we are calculating the sum of all the quantities that are shipped into Albuquerque. For Boston, it's equal to C8, and for Cleveland, it's equal to D8. And again, I will highlight this in blue. Now the outflow from Albuquerque is 0 because it's a pure demand node and there are no arrows coming out of Albuquerque, so that will be equal to 0. The same for Boston and Cleveland, and I will not highlight this in blue because there is no formula in there. The net flow formula remains the same, inflow minus the outflow, and I can drag this down. So now I've populated the left-hand side for my constraint equations. In order to put them in Solver, I need to specify the sign and the right-hand side as well for each of these constraint equations. Oops, I forgot to highlight the net flow in blue because there is a formula in there. Now, because this is a pure balanced transportation model with a transshipment node in it, we can use the equal signs. If it was an unbalanced model, we would have just used inequalities depending on whether the supply is greater or the demand is greater. For the pure supply nodes, Des Moines and Fort Lauderdale, its right-hand side value would be negative, which would include the capacity at each of these. So negative 100 for Des Moines and negative 300 for Fort Lauderdale. Since Evansville is serving as a supply node as well a transshipment node, the net flow for a transshipment node is equal to 0. So we're going to add the right-hand side value of negative 300, which is the capacity at Evansville as a supply node. And then finally, we're going to add the demand requirements for each of the demand nodes. Now our model is ready to go into Solver, and we can put in all the constraints into Solver to get our optimal solution. I've populated the Solver window with the objective function, the changing variables or the decision variables, the constraints, and hit solve. This gives you a minimum shipping cost of $2,600 by following these shipment routes and quantities given in the yellow cells.